thank you to the organization. Thank you for inviting me to have the opportunity to give a talk here. I am a partner, as you presented, in Degree of Freedom. We are structural engineers. We have a focus in architectural, in modern architecture, and we have a focus in timber, in sustainable architecture. We strongly believe in that, and you'll see in the slides I'm going to present that it's a little bit what we like doing more. We have a presence in Spain, in Norway, and here in Greece. We try to do engineering services wherever we can, of course, and in general in Europe we've been touching those countries you can see. And really our special competencies, I have to say, I could mention are steel bridges, timber construction, and complex geometries. The background of most or several of the people in our office comes from our previous experience in the Santiago Calatrava office. You know probably some of the works. I had the opportunity myself to work in this stadium that most of you certainly will know. We afterwards work in other complex structures such as the World Trade Center. We had work in the Turning Torso in Malmo. We have been working in the City of Science since we are from Valencia, most of us, and we had the opportunity to work in that construction too, in the engineering, and some bridges in Reggio Emilia in Italy. So from that background, we, let's say, had the chance to dive into the complex geometries and the projects that are international and complex also from the point of view of the organization of the works. Our services include building structures, bridge design, and also beam and fabrication models, and including also erection sequence assessment. Some of the bridges that we've done, you can see some pedestrian bridges in Norway. On the right side, the suspended bridge won an award in Norway, the best steel construction in 2018. This other bridge was done for Sweden, and we won another award, an architectural award of the area of Eskilstuna. Another pedestrian bridge in Drammen, a bridge in Norway, in Ørje, and our last bridge designed in the office that is going to be built just now. It was awarded to a contractor last month. We've been doing also some projects in coordination or with the collaboration of architects. This is with Mastres Vage. It is in Norway, and it consists in the rehabilitation of some old silos as a museum, an art museum. Here the challenge was to create this big void within the space of the silos. No? This is being constructed, as you can see in the central photo, and it's expected to finish during the year, the structural part of the construction. They are now demolishing the interior part just after reinforcing with a shield what are the silos structure. But I came to speak about timber, and we also do some timber construction. So we love timber. I have liked a lot the previous presentations from my colleagues from the rest of Europe, and it is true that we think that timber is the future. We totally agree with you. And timber is renewable, recyclable, obviously. It has a low energy production. It is health and well-being, but also it has very good fire performance, very good sound absorption. It is a natural insulation, and in brief, it has all the advantages that the world we are moving on requests, no, as a material for construction. No? It's somehow amazing that it was always there, and we were inventing other materials while this has always been there. It is true that modern timber materials are not made only of solid timber, but mixed with other materials, but also glued, which is not that natural. But that being said, we strongly believe in the future of these technologies. Some of the designs that we had the chance to participate on in the past, the two designs on the left side are in collaboration with Snøhetta, and in the other two with other architects in Norway, Saha in particular. All of them were competitions that we didn't win, so we cannot say that it will happen, that this will be in place someday, but they all needed of more than 2,000 hours of engineering only in the competition, no? Altogether, I mean. So we had a certain experience during competitions in the past, and now, recently, we have won our first one as a high-rise building in timber. I hope that we can, we are starting with the design, but I hope that we can proceed during the year with all the concept design, and in the coming years to see that building happening. No? It's done with MAD architects and Bill Energy, and it's absolutely sustainable. The focus is on climate and social sustainability here. It's a 98 meters high building with 29 floors. And of course, it will be the tallest timber hybrid in this case. It's not only concrete, not only timber in Germany, if it finally is built in the coming years. Some views of the building. It has been also mentioned today that timber can allow the current, the current buildings in the cities to grow 1, 2, 3 stories more, which is also a potential need of the cities, because instead of building new buildings and enlarging the size of the cities, we can maybe complete the space within the cities where it is possible. And this is a good example of what is going to be done in Oslo, and we also had the chance to win this competition, and we are going to add four additional floors to this old mall and office building, as you can see in the renders. This is also something we'll do in the future, in the coming months, I hope. But now I'll speak about 3 study cases that were experiences that have been finished and built, okay? So after this long presentation, let's say I will start with the 3 examples that I bring to you today. The first one is the headquarters of a bank in Norway, in Stavanger. It's the Sparebank, and the architects are Helena Har and Saha. We were collaborating with Creation Hold and many others that all together pushed for this unbelievable building to be a fact, to be feasible. It's this is Stavanger, the city in the west coast of Norway, and this is the building. It has a delta shape, 14,000 square meters of timber construction. It has got the certification in BREEAM Nord, outstanding, and today it's the Norway's largest commercial building in timber. It won also some awards, the building of the year in 2019, and the timber structure of the year, and also the Tekla BIM award for Norway and Denmark in 2020. We are also used to do BIM modeling, we work with Grasshopper, and I agree with the previous presenter that it's an impressive tool that allows to change dramatically the way of the flow of work in the industry. The building itself has 7 floors, and it has 2 levels of commercial or the bank where the public spaces are, and then offices on the other 5 floors. The structure itself consists in 3, it has some underground concrete levels in the basements, and then there are 4 concrete cores that are going to block all the horizontal displacements, and then a series of portal frames that will carry are carrying the vertical loads down to foundation, plus the CLT slabs as floors connecting all those portal frames, no? And then on top of that, the skin. The materials chosen were different in the different levels because of the magnitude of the loads. So we chose this glulam made from spruce in the upper columns, and we chose CLT also made from spruce in the floors, and we chose LVL, which is stronger, it's more, the strength is higher, and has a quite different technology of production. And it consists on thin layers, no? In order to produce the LVL material, the LVL composite, let's say, is we peel the tree instead of cutting some lamellas inside, and with those carpets of timber, they are glued, and we reach with that a higher resistance, no? And less, a higher resistance also to shear or rolling shear, no? In the timber. So here you can see the vertical static concept with 2 floors, that public space that I was mentioning earlier, 2 floors that are made of portals with 2 columns and a lintel, and on top of that a space with columns a bit closer and that are continuous from this 2nd floor till the roof, continuous columns and pairs of beams that are allocated or bearing into recesses done in the columns. The frames are every 5.4 meters, and this is the span of the CLTs as floors. The horizontal stability, I've been speaking earlier about that, are provided essentially by the concrete cores, those made in concrete, and all the flooring system made of CLT is acting as diaphragms that transfer all the wind loads in the areas far from the cores to the cores themselves. In this type of buildings, and clearly in this one, we could check that a good modeling of the panels, a good selection of the position of the panels of CLT, and the good modeling of the joints between the panels of CLT was essential to make an accurate estimate of the displacements due to winds, because the panels or the slabs made with CLT are not that stiff as a rigid concrete slab. So it is essential to have a good estimate of this flexibility in order to have a good and accurate values of the displacements in the facades and provide that data to the manufacturers of the facades. No. So that is an experience that we got in this building. The fire resistance, it has been mentioned, and I'm in agreement with that approach. No? Contrary to what someone could think, timber is not a material that it burns. Of course it can burn, but it's not burning immediately. No? So it is safer than steel in many occasions, and it can, in this case, in this building, we did some tests to check this 90 minutes resistance, and it was clear that the size of the carbonized thickness was within what was expected with this type of timber. The finite element model that we developed, as I was just mentioning, it is important to have this paneling to have this slip modulus in between the two, in all the connections, because the connections are going to slide a little bit, and this has an impact in the final movements of the building. And we were using some non-linear links for that, and to be accurate in the timber mechanical characteristics. Several software do that relatively easily, so it's not something that it is new, but nothing really challenging today for an engineering office. The deformation, the horizontal wind was clearly maximum farther at the farthest point from the cores, and you can see it in the blue area. And there we had these checks, no, that need to be shared with the fabricators so that the facade could allow for those movements. We had also made some comfort studies for some of the areas, because we got in this building also some cantilevers vertically, for the vertical loads, I mean. And at those areas we were checking the accelerations, etc., for a normal office use to be within what the regulations require. And some other area which is special, the stairs, which you will see some photos now. The stairs are kind of sculptural elements in the atrium, and those stairs are made with timber, this LVL with timber, but that has been curved in two directions. They have double curvature. And we did some tests, of course, in finite element model to again check that the walk in those stairs was going to be comfortable enough. This is a few slides about the erection sequence and the process of fabrication. We were providing this beam model that was used for the fabrication, and then the CNC machine was cutting the holes, all the recesses, and here you can see also some lamellas that have a different color, and those are stiffer lamellas of LVLB at the areas where we needed to carry the load of the beams on top of the columns. No? So at the recesses of the columns, we were using those stronger lamellas of timber in order to transfer those stronger loads. So it can be combined. The timber is also very, with timber it's also very easy to combine different types of timber, different technologies of fabrication of timber all together, either glued or connected with screws or whatever. These are parts of the stairs, and as you can see, it was curved. No? They were using this technology I was mentioning, and then they were curving all the different lamellas and then gluing together to obtain those shapes. The erection, it was done really fast. I don't have the data about the number of weeks, but certainly it was relatively fast. Although this building, as you can see, it's not really an example of fast fabrication, since the details of connections and the shapes themselves are relatively complex. They are not a standard timber building. But it was fast, and certainly the contractor was doing all the concrete works while working in the shop on the timber, and then bringing all together in one shot or as fast as possible. Some other slides of during construction process, we were also involved in the erection and the means of stability during the erection. An important thing when these timber structures are interior or are made of timber thought for the interiors, they have to come protected and they have to stay protected while the building has not the facades ready, no? Or installed. So this is relatively simple with some plastic protection, but it is important to keep it, no? And you can see in the images that there is a lot of protection on the timber sizes. This is one of the stairs that was put in place, and on the right side you can see several of them, or the 4 of them, already installed. all the lighting and architectural finishes inside, plus the positioning of the roof at the final stage, and some views of the building finish. So on the right side, you can see the area where the cantilevers obliged us to do a specific evaluation about the comfort of the people on top of those. And on the left side, a view of the building where it has the 7 floors of timber. The stairs in the atrium as they look today, and this other corridor at the public spaces of the building, where the portal frames cover two levels. A space above, and here you can see also how warm is the atmosphere with timber construction, or even if the timber structure is exposed to view. This is another building. It has nothing to do with the previous one. We did it a bit after, and we did it with the same architects, Helen and Hart, and in a collaboration with Creation Hall. It is a bibliothèque, but also it is a urban passage. So the architects, the location and the spot where it had to be built was almost circular, and the architects thought that it could be the bibliothèque as a place that gathers literature and people, and also a urban passage from a street to another, so where you can shortcut and take a while to stay and read a book. So the proposal was on the shapes was from the architects, and our collaboration with them was about making possible the engineering of all of that. Here the building has only 4 levels in total, and we used several timber qualities also, and several technologies of this timber. But in essence, the key feature of the bibliothèque are these portal frames that you can see on the top part, where we had like two big columns and a tie on the left side, because it's really in tension, this element, and we had to use curved elements in the lintels in order to orientate the fibers of the timber in the correct direction. So the lintel has been curved, or has been made of curved lamellas glued together, while the columns have been made of straight lamellas. And the tricky thing here was the connections, and especially the one on the corner, because these portal frames, in order to be stable laterally, required in this specific building of a certain rigidity. It could not be just hinged beam to beam or column to beam. And that's why we had to use pairs of connections in the corner in order to provide this rigid connection at the portal frames. We had in a different part of the building, the same building, we had 2 levels of apartments and a small bank office. And those areas are made with CLT panels. So here we have, at the bibliothèque side, portals made of glulam and CLT as slabs between portals orientated in a circular manner. But on the other side of the building, we have a CLT building similar to the ones shown by my previous colleagues here, but orientated again in a radial configuration, since the building is almost a circle in plan. It has also a tricky thing here, which are those balconies that you might see on the left side that were cantilevering from the inside, and that obliged to orientate the CLT panels in the correct direction, because the CLT panels, even if they are shear walls or 2D elements, they have a preferred direction for bending, the one with the fibers of timber orientated in the external layers. We did here again, our structural analysis, the infinite element model, and that was done a bit later, and we here took the opportunity to create our own post-processor for all the timber to timber and all the timber to concrete connections that we got in the building. This building has a core, the lift elevator, which is also made with timber. So below you can see some screenshots of the results that this post-processor made with MATLAB was showing. It was very visual and very clearly you were identifying the points where you should put a larger density of connections. The connections again were simulated with the correct stiffness from the predetermined connection and then checked. Some views of the building. So this is the space as it is today. This is the bank that in the other side of the building, and that has the apartments on top of it. You can see the curve space, the curve elements. And we can see here the central atrium, which is circular and provides light to the bibliothèque, to the building. Some views from the external, and I move straight forward to the last example I bring today. So this is a collaboration with Dark Architects and with Betonmas. Betonmas is a contractor in Norway, and Betonmas was the client of all of us. No? The architect was Dark, but we were working for the contractor. So here we were doing also the model for the fabrication for the contractor. This is in Drammen, another city in the south of Oslo. And here one of the interesting things, it's a 10 floors building in timber on top of a foundation that has below a very poor quality soil. We had rock at 100 meters below the ground. And there in Norway, when the ground is that poor, you need to pile down to the rock. You are not allowed to pile just some meters. You have to reach the rock. So we had 100 meters long piles below the building. So, and the building was needed for, the building needed of weight as light as possible in order not to have a huge foundation. And that's why we were estimated several alternatives in the beginning, and we concluded that we could save like 1 million euros only by the fact of using timber in the structure instead of concrete or steel, or a combination of both. And that was one of the reasons that this project went on with timber. But the building is there. The building is relatively simple when you compare it with the previous cases that I have shown, but still the nice thing for us was that it was the tallest we did, and still it is the tallest office building in Norway today. No? There are tallest buildings in Norway, an 18-floor tall building, but this has another use. And here we did a digital twin of the building that was used by Betonmas, by the contractor, to compare what is on site with what should be, no? With the digital twin. And they were scanning the reality every week and comparing to the model. This was erected, the 10th floor, in 15 weeks. So here I bring a case where, as it was mentioned earlier, the fabrication was really fast, and in 1.5 weeks per floor, it was done everything. We did also a physical model of the building. This is what you can see here, the beam model that we performed, and 2 images of the timber physical model at a certain scale. I don't remember which one, but this is. And here we used massively CLT as a product. No, we were using, certainly for the floors, 200 millimeters thickness, if I'm not wrong, and for the cores that we're going to resist or are resisting all the horizontal forces. The cores are made with CLTs of a thickness of 260 millimeters, connecting 4 columns made with glulam that strengthen the corners of the cores. All together connected make the box that is the central core. And around the cores, we have a series of glulam columns and beams that support on its turn the CLT slabs. This is another image of our model, the twin model I was mentioning. You can see on the blue image the holes for the pre-drill of the screws, so that we were having that level of detailing. We were even positioning the holes of the screws that the machinery should drill on the shop, so that when they arrive on site, they have already the hole to put the screw and not being like trembling or facilitating the connection. So we worked really in a very close and good collaboration with Betonmast. The assembly drawings that we were producing, quite standard, let's say. And here's some details of the building. The concept of connection beam to column is similar to the Sparenbag, to the first project I was showing, but here, let's say, a bit simpler, because the building is simpler in its as overall. No? We have these double beams on top of recesses on the columns. Some other details where you can see the finishes and the picture of the erection, how these columns are continuous and the beams are around them. Some images of the connections. In general, the timber to timber, in a large majority of the connections that we were used, the timber to timber was in compression. No? Column to column was largely a compressed union, and the same with the beams to the columns in the recesses. No? So in general, the number of steel plates was reduced to a very, very limited number. But here you can see some of the cases where there was some uplift, we were connecting also in case, just in case. No? Some pictures of the erection, I'm finishing now, and another details of the building inside. I want to finish by informing you that we have here with us, I don't know, Knut, a representative of the next conference about timber construction and engineering that will happen in Norway in 2023, and maybe you can tell them quickly what is going on there, because we are silver sponsors of that conference, and I think that it is something interesting that I would invite all of you to participate. And that's it. Thank you for attending.